Hi, this video is about properties of solutions. All right, first of all, let's review what a solution is. It's a homogeneous mixture, and it's comprised of two parts. There's a solvent and a solute. The solvent is what's present in the greatest amount, and the solute is present in the lesser amount. So far in chemistry, we've worked with a lot of aqueous solutions, and that's that AQ after something in a balanced equation. That just means that the solvent is water. But the solvent can be it can be other things. And so how can you identify what's a solvent in a solution? And so here's an example. You have 0.64 grams of adrenaline in 36 grams of carbon tetrachloride. So what is the solvent? So we're looking for what is present in the greatest amount. And so if we look at the question, we see that 36 grams of carbon tetrachloride is the greater amount, so 36 grams here. So carbon tetrachloride is our solvent, and our solute is the adrenaline because we have less of that. So the adrenaline is the solute, and carbon tetrachloride is the solvent. All right, well, this video is about colligative properties, and those are the physical properties of a solution that depend on the total number of solute particles present. Doesn't matter what they are, just how many you have. And so the colligative properties that we need to learn in chemistry, we need to talk about vapor pressure, we need to talk about boiling points and freezing points. This video is going to concentrate on the vapor pressure. So the first thing we need to do is identify what is vapor pressure. And so here we've got this animation, and here we've got these molecules, and we'll just go ahead and say that it's a solvent that is water. And so these, as you can see, these water molecules are evaporating and they're condensing back down. It's a closed system, which means that we have a lid on the top, and then it is building up some pressure and that is shown here with this manometer. And the vapor pressure is the pressure of the vapor above any liquid. But it is the vapor pressure above any liquid when the rate of evaporation of the liquid equals the rate of condensation. And so you may want to pause the video and get that definition down. The vapor pressure is the pressure of a vapor above a liquid when the rate of evaporation of the liquid equals the rate of condensation. So the definition is here in the orange and purple text. Okay, so vapor pressure. What do you think temperature would do to the vapor pressure? So let's go ahead and choose 15 degrees Celsius. Notice that the water molecules are moving slowly. They're hitting the sides of the container. That's what causes the pressure. They're not hitting them as frequently. Now watch what happens to these at 50 degrees. At 50 degrees, the water molecules are hitting the sides of the container more frequently and with more force. At 15 degrees, because the kinetic energy of the particles is so much lower, they're hitting the walls less frequently with less force. So how does temperature affect vapor pressure? Well, as you increase the temperature, the vapor pressure will also increase. All right, let's go ahead and try this little problem here. Okay, so let's go ahead and make our solvent water. And we're going to have, we'll have 60 grams of water. Okay, we're going to keep it at 25 degrees Celsius, and let's add some salt to that water. And let's see, how much do we want to add? We'll add, 40 grams of salt. Okay, now let's look over here. Right now, we haven't added the salt yet. Okay, and the vapor pressure is 23.76 millimeters of mercury. That is the vapor pressure of water at 25 degrees Celsius, of pure water. Now, when we add the salt, there we go. See, we dumped it in. All right, over here, now, see those orange molecules here? Those are the solute particles. Notice that they are not evaporating into the liquid state. We say that our solute is non-volatile, and that's important because we don't want our solute to be evaporating and adding to the vapor pressure. But what happened to the vapor pressure with our water molecules? It went down. It went down. So when we added our solute, the vapor pressure of the solution went down. So let's think about why. Okay, so the population of molecules here that are causing vapor pressure has gone down. Okay, the percent of molecules that are causing vapor pressure went down. And so our vapor pressure went down. All right, so let's go ahead and let's go back and see if we can summarize what we have learned. All right, so let's go ahead and say that the vapor pressure is decreased by the presence of solute particles. All right, and hopefully that statement makes sense now that we saw that animation. All right, the solute particles should be non-volatile, so they are not evaporating into the liquid state. And then as you increase the number of particles in solution, even though I didn't demonstrate that, the vapor pressure will continue to decrease. As the population of particles in our solution that can evaporate goes down, so will the vapor pressure. And then as you increase the temperature, the vapor pressure will increase. And the reason is, and I want you to understand the reason why temperature increases the vapor pressure, it's because the gas molecules are moving faster. They're hitting the walls of the container more frequently and with more force, and that's what's causing the pressure. So please make sure that you know this summary slide and understand it. All right, so how much will that solute lower the vapor pressure? So let's talk about it quantitatively now. All right, well, there's an equation for that. Of course there is. It's chemistry. All right, so guys, the vapor pressure of our solution is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. Okay, so this is the vapor pressure of the pure solvent. And you could look that up in a table. It's of course going to depend on the temperature. Okay, and oh my goodness, mole fraction. We may or may not have talked about this depending on which order you watch the videos. So mole fraction is equal to the moles of the solvent, if we're looking at the mole fraction of solvent, divided by the total number of moles. So that would mean that the moles of solvent plus solute. Okay, so if it's pure solvent, the mole fraction would be 1. And so the vapor pressure of the solution is the vapor pressure of the pure solvent. But as we add solute particles, this mole fraction is going to start to become less than 1. And so the vapor pressure of the solution will be like some percentage of the vapor pressure of the pure solvent. This is known as Rayoult's law. And it's actually quite easy to do. All you have to do is calculate a mole fraction, and you multiply it by the vapor pressure of the pure solvent that's given, or you look it up in a table, and you've got the vapor pressure of the solution. And it should always be lower than the vapor pressure of the pure solvent. All right. I think we should practice that. All right, so let's calculate the vapor pressure of water above a solution prepared by adding 22.5 grams of lactose, and there's the formula for lactose, to 200 grams of water at 338 Kelvin. The vapor pressure of pure water at 338 Kelvin is 187.5 torr. Okay, so there's our vapor pressure of the pure solvent. Now, whenever we add anything to water at that temperature, the vapor pressure is going to be less. Our answer is going to be less than 187.5 torr. Okay, so if this is multiple choice, if you see an answer that's greater than 187.5, don't choose that one. Okay, but now let's find out the real answer. All right, so the vapor pressure of the solution is equal to the mole fraction of the solvent, so that is of our water, times the vapor pressure of the pure solvent. So look, let's calculate the mole fraction of our water. All right, so we need total moles of water. So we got 200 grams of water. If we divide that by 18.02, which is the molar mass of water, and I've done this ahead of time, I get 11.10 moles. That is our solvent water. And then when I go ahead, the molar mass of lactose here is 342.34 grams per mole. So if I get my total moles in 22.5 grams of lactose, I get 0.0657 moles of lactose plus 11.10 moles of water. So this is the lactose. This number comes from 22.5 being divided by the molar mass of lactose, which is 342.34. You know what? Let me go ahead and do that. Moles of lactose is 22.5 grams. And when we do the molar mass, so 12 carbons, 22 hydrogens, 11 oxygens, that's a big boy of 342.34 grams. And the answer here becomes 0.0657. Now, keeping in mind our sig figs here, the mole fraction would become, let's see, 0.99. Okay, so the mole fraction of the water is 0.99. And now let's get the vapor pressure of the solution. It is going to be 0.99 times 187.5. And our final answer is 186.3. So that is our final answer. Final answer is 186.3 torr, and that is lower. So the vapor pressure of our solution was lowered by the addition of our solute 22.5 grams of lactose. Alrighty, so we're going to practice this some more. So we now know how vapor pressure is affected by solute particles. Our next video will talk about boiling points and freezing points.